Hey there, welcome to Dig into EVM, I'm Aurélien, and today in this video I'm going to be showing you how you can deploy Uniswap V2 onto your local testing environment using Foundry in only 30 minutes. We're also going to be deploying an ERC20 token, adding some liquidity, and by the end of the video I'm also going to be showing you how by only changing 2 lines of code, how you're going to be able to port all of your tests from your local testing environment to Ethereum mainnet or any other EVM blockchain of your choice. So I hope you guys are ready, let's go. Before we start, I assume that you guys already have Foundry installed on your computer. If it's not the case, feel free to pause the video to check out some YouTube tutorials on how to install it. The installation process will not be covered in this video as it is outside of the scope of this tutorial. Alright, so now that we all have Foundry installed, let's create a new directory. I already created mine, it's called local Uniswap. It's going to be hosting the project. Now let's use Forge init. This is going to be cloning the default Forge repository for any project. Now you can see that we have some default files and directories that were created. This is the example project. It contains 3 smart contracts, one in script, one in SRC and one in test. I'm going to be deleting them because we're not going to be using them inside of this tutorial. Now let's go ahead and install our dependencies. We're going to be using 4 dependencies here, 3 from Uniswap Git repository and 1 from the Soulmate repository. When installing dependencies in a Forge project, you can do it with the regular npm way, but I personally prefer to use Forge install. You may use whatever you want, but keep in mind that the remappings that we're going to be doing after the installation of dependencies might not be matching your exact path. Here I'm also using the no commit flag. This actually prevents an error from coming. You can also solve this error by just staging all the files. Okay, so now that we're done installing our dependencies, you can see that they're currently now located inside of the lib folder as well as the Forge std default dependency. Alright, so now I'm going to be creating a new file which I'm going to be naming remappings.txt. This file is actually going to hold our remappings. I will be writing 3 of them. Here again I'll be writing them down inside of the description, so you can just go there if you want to copy paste instead of writing them manually. Now let's use forge build. This is the command you want to use in order to compile a smart contract. Here, note that there is nothing to compile simply because there is nothing inside of our script, SRC or test directories. Smart contracts that are located inside of libraries are not counted and will not be compiled unless you import them in one of your smart contracts. Now let's create our first smart contract inside of the script directory. I'll just call it imports as it is in fact not a real smart contract. We'll just be using it in order to compile our factory and router, which is the reason why we are using an old solidity version here. Now that we've imported both our factory and router, let's try to compile that. Here as you can see, the compilation failed. This is because in fact these 2 smart contracts are not compatible with each other because of some solidity version requirements. We can actually fix that pretty easily. All we need to do is actually to comment an import, doing forge build in order to compile the first half of the smart contracts, and you can see that inside of the out directory we can see all the artifacts of the smart contracts that we just built. Now we just repeat this operation with the other import and we're ready to go. Now let's go ahead and create our Uniswap deployer smart contract. This is the smart contract we will be using in order to deploy the Uniswap V2 onto our local testing environment. This time we can use a recent version of Solidity. We're going to be using here 0.8.5 as we don't need anymore to build any old Uniswap V2 smart contract. Our Uniswap deployer smart contract is going to be inheriting the script smart contract which is provided by Foundry in order to let us use lots of useful tools. So we also need to import it from Forge std. When writing a script smart contract, Foundry is expecting that there is a run function inside of it. If you don't include it, nothing will be executed because this is the function that's going to be called and we need to put all of our logic for the script inside of it. In order to deploy our old Uniswap smart contracts, we will be using deploy code 2. This is provided by Foundry and this allows you to actually deploy compiled bytecode to a specific address. To be able to use that, we need to import std cheats from the Forge standard library. Now that we've imported the std cheats library, we'll give the inheritance to our Uniswap deployer and we'll finally be able to use deploy code 2. Now we need to input the smart contract file as well as the smart contract name in order to tell Foundry that you want to deploy Uniswap V2 factory from the Uniswap V2 factory.sol file. This function takes a second argument, which is an address, and this is the address that we want the compiled bytecode to be deployed at. Let's use here the Uniswap factory address that's deployed on mainnet. If you're trying to deploy a smart contract that's having a constructor which is taking arguments, you can also include these arguments into deploy code 2. This is easily done by using abi.encode, and then you just input all of the parameters. Here in our case, with the Uniswap factory, we need to input an address which is going to be the V2 setter. In our scenario, we don't really care what this address is going to be, so I'll just input an address 5555 and this will be good enough. Now let's execute our script. We can do that by using forge script and the path of our script. Now, as you can see, the deployment failed. If this also happens to you, you should just recompile another time the factory and should be good to go. Now that our script executed properly, let's go ahead and create our first test smart contract. I'm going to be calling it uniswap deployer.t.sol. We're going to be using it in order to check that the deploy smart contract was correctly initialized. Now our Uniswap test smart contract is going to be inheriting from the test smart contract provided by Foundry, which is also a set of tools, and therefore we again need to import it from the forge std library and give the inheritance to our smart contract. Unlike the run function inside of scripts, here the setup function is not mandatory, but if you want to do any kind of setup before running test, you need to do this function. It's going to be called before calling any of the other test functions. When writing tests, keep in mind that they are executed separately. I mean by that forge, when I'm going to be running some tests, before calling the test one, is going to of course call the setup function, then executing the test one, and at this point is going to be flushing the testing environment that it just created, run the setup function again, and then run test 2. What you're going to be doing in test 1 will not have an impact in test 2. Here in our setup function, we want to be able to create a new instance of our Uniswap deployer function and be able to execute the run function inside of it in order to deploy our factory. So let's import our Uniswap deployer from our script directory and let's create a new instance of the smart contract using the new keyword. Now that we're done with the setup, let's go ahead and create our first test function. I'm going to be calling it test Uniswap factory, but you can call it whatever you want. Just make sure that the name of the function includes test, as this is how Foundry will know that this is a test function and this needs to be executed as part of tests. Now we need to find some kind of way to validate whether or not our factory was correctly initialized. In order to do so, we can take a look at the Uniswap factory smart contract, and by looking at it, we can see that there is an address public v2 setter variable. This is actually the variable that we set upon deployment inside of the constructor, and we can simply assume that if we're calling this variable, then it should not return the address 0. If we're returning the address 0, then it means the initialization went wrong. Inside of test function, we usually use assert, which will revert the transaction if the condition inside of it will not be evaluating to true. First of all, let's actually import the interface for our Uniswap factory. Here, make sure that you actually import the interface and not the smart contract, because if you're importing the smart contract, the contract will not compile anymore. Let's also instantiate our factory inside of our test smart contract with the address to which we deployed it, so that Solidity can know where to find it. Now we can assert that the v2 setter function from the Uniswap factory that we deployed should not return the address 0. Let's actually try that by using forge test. Now you can see that this fails, but this is not a fail because of the test. This is a fail because Foundry cannot find some artifact. This can happen in some test smart contracts. If this happens to you, we just need to go to foundry.toml file and add unchecked cheat code artifacts and set it to true. When that's done, let's run the test again and it should pass. When running forward commands, you can add -v in order to add some verbose and see more details about what's going on. You can add several of them in order to have more and more details, the maximum being 4. Here you can see that the test passed and you can see some details about it. You can see that we called indeed the factory that we deployed, we called the v2 setter function, and you can see that the return data is not the address 0. Actually, is the address, this is the hexadecimal representation of the address that we set with all the 5 before. Now that we were able to check that we correctly initialized our factory, let's go ahead and see what we need to be able to deploy our router properly. Now that we're looking at the smart contract of the router, we can see that the constructor takes two arguments. The first one being the address of the factory that we just deployed, and the second one being the address of the wrapped ETH. Actually, we have not yet deployed the wrapped ETH, so let's start by that. Now, in order to deploy the wrapped ETH, we need to import it inside of our Uniswap deployer smart contract. So let's import it using the Soulmate dependency. Since the implementation of the wrapped ETH provided by Soulmate is made on a recent version of Solidity, we could deploy the smart contract using the new keyword. But this does not give you any control to the address to which the smart contract is going to be deployed at. That's why we're not going to be doing that. Instead, we're just going to be keeping the import in order to be able to compile the smart contract, and then we'll be deploying it using deploy code 2. Now that we successfully compiled the wrapped ETH smart contract, let's go ahead and write the deployment function. Let's use the real address of the wrapped ETH on mainnet. The smart contract does not take any constructor argument, therefore we don't need to input any. Now let's take a look at the smart contract to see how we can validate that we properly deployed the smart contract. Going inside of it, you can see that this is inheriting the ERC20 implementation. So if we're going there, we can see that we have a bunch of variables available for us, and we can use one in order to be able to validate the correct deployment. Here, let's use the name. We can now remove the import of the wrapped ETH from our Uniswap deployer smart contract as we already compiled it. Now let's go ahead inside of our Uniswap deployer test smart contract and let's write our test function to test the deployment of the wrapped ETH. Let's instantiate our deployed with variable so that Solidity knows where to find it. Here we're using the contract like an interface. We're able to do that because Solidity will not have any issue since the smart contract is made using a recent version of Solidity. We're not deploying again a smart contract here. By doing that, we're just using it as an interface. In Solidity, strings don't really behave the same as in many other languages. So to actually check whether this string is null or no, we can just use abi.encode to explicitly convert this string to bytes and check the length. If we have more than 0 byte, then it means that the string contains something and therefore that the deployment was successful. Now let's not forget to import the wrapped ETH inside of our testing smart contract. Since the wrapped ETH contains some payable functions, we also need to make it payable here in our instantiation. Now let's run forge test with some verbose in order to be able to see whether the deployment was successful. And here you can see that we're pathing both tests. You can see also that we called our wrapped ETH address with the name function selector and that the return data was the string wrapped ether. So perfect. Now we should have everything we need in order to be able to properly deploy the router. So let's go back to our Uniswap deployer script and write the deployment code. For the deployment address, let's again use the real deployment address of the router on mainnet. Now let's take a look at the constructor arguments so that we can input them in the correct order. So we can see that we need to input the factory and then the wrapped ETH address. So let's do. Now let's go again in our testing smart contract and let's write a function to be able to make sure that we correctly deployed and initialized our router smart contract. Here let's take a look again at our router smart contract and let's see what we can call to validate the state. Here we can call the wrapped ETH address, which is the address we input inside of the constructor. If this address is not 0, then it means it's correctly initialized. First, let's actually import the interface for our router. And here again, just like Uniswap Factory, make sure you are importing the interface and not the smart contract. Otherwise, you're not going to be able to compile anymore. Let's also instantiate our router address so that Solidity knows where to find it. Let's now run forge test again to make sure that the test we just added is also passing. And here we can see 3 passing tests, that's perfect. If we're taking a look at the test deployed router, we can see that we called wet onto the contract address, and it returned the address of the wrapped ETH smart contract that we deployed and input inside of the constructor. So we can definitely validate that it's properly initialized. Now that we have Uniswap onto our local testing environment, let's go ahead and create a token so that we can create some pair and add liquidity. I'm creating a new smart contract inside of the src folder. Let's call it token.sol. This smart contract is going to be called token and is going to be inheriting the ERC20 implementation from Soulmate. So let's also import it. Now let's take a look at the ERC20 smart contract. We can see that the constructor takes 3 arguments: the name, the symbol, and the decimal. Also note that there is no minting mechanism already in place, so we'll have to implement it into the constructor of our token. Let's take a look at the mint function. You can see that here we're increasing the total supply, we're increasing the balance, and we're also emitting a transfer event. So that's perfect. Now as the name, I'm gonna give Turbo Mooner so that we're sure to print fast, TBM as a symbol, and 18 as the decimals, to be original. Inside of our constructor, we're gonna be calling mint function. It's gonna mint to message sender, which is gonna be the test contract, and let's say that we're gonna be minting 1 million token. Now let's go back into our testing smart contract. Note that we're not going to be deploying our token inside of the Uniswap deployer smart contract because this contract is only for Uniswap stuffs. Okay, instead let's go and write a test in where we're going to be deploying this contract and add liquidity. Let's also not forget to actually import the token inside of our contract by going out of to directory, src, and token.sol. We are deploying our token inside of the test add_liq token function and using the new keyword. Here we don't really care to what address the token is going to be deployed at, this is just part of a test. Alright, now let's call our router to be able to add liquidity for our token. Note that here I don't have access to all the attendances of most functions. This is because in our testing smart contract we implemented the router using the Uniswap V2 router 02. But in fact, most of the functions are inside of the Uniswap V2 router 01. The second version, even though it's still Uniswap V2, has been made in order to be able to handle fee on transfer tokens. But the function in which we're interested in right now is add liquidity ETH, but it's available in the router 01. So let's import it. Now let's wrap our router inside of this 01 interface. And now you see magic. We have access to all of the functions, and the one we're interested in right now is add liquidity ETH because we're going to be adding liquidity in Ether. Now we need to add value to our message. So here I'm just going to say that the value is going to be 10 Ethereum. Then the first parameter is going to be the address of the token, and the second one is going to be the amount of token with which we want to be adding liquidity in the ratio. So here I'm just going to say that we're going to be adding the amount of the balance of the current testing contract because this is the contract which received the mint of 1 million token when we actually deployed it. I could just hard code here 1 million, but I like to keep my code flexible, and here even though it consumes a tiny bit more gas, I prefer it that way. So here the third and fourth parameters are slippage related. Here I don't really care, I'm just going to put 0 for both. We are running it on a local test environment and therefore nobody's going to come and front run us, so we should be fine with it. Then the fifth parameter is going to be the address 2. This is in fact the address which will receive the refund in case that all of the tokens or of the Ethereum were not able to actually be added to the liquidity. In that case, since we are creating a new pair, we're going to be the first liquidity providers, therefore the ratio we're going to put is going to be a perfect one and we're not going to be refunded. But if for example you're calling this function and you're not the original liquidity provider, make sure that you have a fallback or a receive function in your contract, because this can revert you if the router is actually trying to refund you some ETH. As the deadline, we're going to put block the timestamp plus 1000. Here again, not very important. Here, by the way, the router, when we're going to be adding liquidity, is going to try to use transfer from in order to get tokens from my address. Well, here, not really mine address, but the address of the testing smart contract. Therefore, if we don't approve it, it's going to revert. So here I'm just going to be actually approving for the maximum amount. Here again, it's a testnet, we don't really care, but of course in real it's highly advised to use only the amount of allowance that you want to actually allow. Also, I forgot to mention, but here we are sending a message with 10 Ethereum, but we did not actually provide the contract with any Ethereum. This is because by default Foundry is going to provide Ethereum to the testing smart contracts, but if you want to give any other value, you can give the flag initial balance, and then the contract is going to be provided with this balance. Alright, so now we're pretty good to go. Let's go ahead and do forge tests in order to test the add of liquidity. Here you can see that the test actually reverted. This was expected, but I actually wanted to show you the example. Here we can see that in the details, we can see the approve, we can see that the balancer returned the expected value, that the pair was created, and there was the pair created event even emitted. So here, in order to understand what happened, let's go and check out the router smart contract once again. Let's go check out what's inside of the add liquidity function. We can see that we're getting the pair to check if it exists, and if not, we're creating it, and then we're calling this library. You can see that we have a get reserves function, which is calling pair4. And the get reserves function is the function that we are actually calling inside of the router. If we're taking a closer look at the pair4 function, we can see in the commands there, that's why this function is pure. This is meant to save a bit of gas. It cannot actually do any external call. So what it's actually doing here is that they are using a simulation to recalculate an address generated by Crit2. The Crit2 opcode allows you to deploy a smart contract on an address that you can calculate in advance. This is very convenient in some fields, but the problem is that the address that you're gonna pre-calculate is gonna change drastically according to some parameters. For example, if the factory address is not the same, it's gonna change. And here the problem is that it's also going to be changing if you don't have the same hash for the bytecode. Here, the hash you can see is actually the checksum of the bytecode, and the guys from Uniswap hard-coded it like that because they compiled themselves the pair smart contract. But the thing is that when you are compiling a smart contract, you are gonna have kind of three parts inside of the bytecode. You're gonna have the initialization bytecode, which is gonna hold like what you have in the constructor. You're also gonna have the runtime code, which is the code at the address, and you're also going to have some metadata. The problem is that this metadata is going to change according to the machine on which you are compiling the smart contract. The thing is that since I recompiled the smart contract of the pair, I changed this part of the metadata of the bytecode, and therefore this hash is not correct anymore. And this is why the pair4 function is not able here to recalculate the same address that the factory generated when it deployed the pair with the Crit2 opcode. So there's actually an easy way to fix that, and I'm gonna be showing this to you guys. Now some people, they would just erase everything that's in the pair4 function and they would just replace it and call the factory to get the exact address, but I'm gonna show you how we can change the hash so that we don't need to change anything else and be as close as possible to the real Uniswap. So in order to do that, we need to go in the compiled artifact directory, which is the out directory. We need to find the Uniswap V2 pair.sol directory, and inside we have this JSON file, which is the artifact that we generated upon compilation. In there we need to find the bytecode. Okay, this is this whole big chunk of data. Make sure you are taking the bytecode and not the deployed bytecode, because these are not the same, and we need here the bytecode. Once you copied the bytecode, we just need to go and hash it. We can use many tools. Let's use an online tool. You can use the same as I'm using right now. I'll put the link in the description. Here, just make sure that you are selecting input type hex and not UTF-8, and also you need to remove the 0x that's at the very beginning of the bytecode, and then you're going to be able to have a new hash, which is the one we need to change inside of the smart contract. So here, copy the new hash. Let's go again in the library, change the hash that's there with the one you just generated, save the file, and now we're gonna need to compile again. So for that, let's go back to our file import.s.sol. Make sure that you have the router uncommented, because this is the one that is linked with the library, and therefore this is the one we need to recompile. Let's do forge build again so that we can recompile the library, and then we should be able to run successfully our test with forge test. And here we go. You can see that we are now passing all the tests since we changed this hash. Alright guys, so before we end this video, let me just show you two more cool things very quickly. Let me run a new instance of Anvil. Anvil is the EVM machine, let's say, that Foundry is providing you. This is some sort of local blockchain that you can run on your computer. This is pretty much for test environment. It's not really a real blockchain, but of course it behaves like the EVM blockchain, but it also supports all the cheat codes and the cool stuff that Foundry gives us. Alright, so now let me just put it on the side, and you're gonna see that if I run forge test again, we're not gonna be seeing anything inside of the terminal, because the environment in which Foundry does all the testing, it's another environment. It's not exactly this one. It's an environment that it's creating just when you're doing forge test or forge script, stuff like that. But you can of course provide an RPC URL in order to say to Forge, okay, I want you to be running this test on this RPC. So here I'm gonna show you what happens when I'm putting the RPC of the local EVM Foundry gives us. And when I'm running the test, you can see that we get a bunch of logs in there. We're getting get code, get storage at. It's because Foundry is kind of doing a fork of this blockchain by simulating state changes and stuff like that. Of course, we are not here deploying anything onto this local node, but we could. This might be the subject of another video if you guys are interested in it. So now I'm gonna show you the cool stuff. For example, if I go in the setup function, which is the function, if you remember, that is deploying our Uniswap locally, if I command that and if I'm running the test again, it's gonna fail. Of course, as you can see, everything is reverting and no test actually passes. This is because this time, since we commented what's inside the setup function, we're not deploying any factory, we're not deploying any router, any wrapped ETH, we're not deploying anything, so nothing can work actually, which is kind of logical because that's how it should work. But the fun thing is that if, for example, I take an RPC from Ethereum mainnet right now, let's go on some website to take the fastest one, I can keep the setup function commented, so we're not going to be deploying anything. But if I provide this RPC, it's actually going to be doing the simulation here by simulating the state of mainnet inside of our local environment. So here, of course, it's a bit longer because it needs to do a lot of calls. And here, as you can see, all the tests now pass again, even though we still kept the setup function commented. And this is the reason why I wanted to put all the addresses for the router, for the wrapped ETH, for the factory, the same as those on mainnet, because with this implementation right now, you can actually test anything you want locally, because you, for example, if you want to test your logic, your business logic and stuff like that, you don't want to be wasting time every time to call an RPC to test, etc. So you can pretty much run everything, like you can deploy your tokens and stuff like that, test them locally, and when all your tests satisfy your expectations, you can go ahead, just comment the setup function, give the RPC of mainnet, and go ahead and actually test your contract just like if it was on mainnet, with changing 2 lines of codes. So this was my point with that, and now you probably understand why I wanted to put this address instead of just deploying everything at undetermined addresses. So that's it for this video, guys. This was, by the way, the very first video of the channel, so if you liked it, please put a thumb, comment if you have some suggestions, some feedbacks, if you like the content. If you're into this type of stuff, like EVM related development, feel free to subscribe to the channel. I'm gonna be trying to provide you guys with some good content about EVM. We're gonna be doing some Solidity, we're gonna be doing some Huff, some inline assembly, maybe some Golang. I'm actually learning Golang right now. Might be cool to show you some stuff with it. Might be also doing some TypeScript, which is a language in which I have way more experience. But yeah, guys, thanks for watching and see you around.